Good day, everyone, and welcome back to my pre-calculus class. Last time we were looking at inverse of trigonometric functions, and I explained that for us to be able to find the inverse of a function, the function has to be one-to-one. That is, it has to pass the horizontal line test. However, we found that the cosine function, the sine function, tangent function do not pass these tests. And then we discuss restricting their domain to enable us study uh, their inverses. For example, if we have sine graph, we say we can, okay, I can extend this here. So we say we can consider this domain. That is, we restrict it to this interval. And we have something that will allow us to find the inverse of a sine function. For that, we say that is from negative pi over 2 to pi over 2. And that allows us to find, uh, to evaluate problems like this. Problems like this. We've done that in our last class. The same thing with cosine and tangent. Today, we want to proceed uh, by using the same idea. However, now we want to look into compositions of trig functions. Now, to start this, recall, let me remind you something you have learned in the past. If we have a function that behaves this way, say we have a function, I call it f, say this is A, B, C, D, 1, 2, 3, 4. Then if I map A to 1, B to 2, C to 3, and D to 4, my claim is that this function is one-to-one. So you can see every output value is having just one input value. Okay, now this graph, sorry, this function has this property. Let me show you something. If I have f inverse, so let me draw this function this way, f inverse. Okay, okay, if I have, this is graph of f inverse. Now, the domain, I will have something like this. That is the inverse of f. So A, B, C, D. And I map this to this, this to this, this to this, this to this. We learned that in our last class. For inverse, the domain becomes the range and the range becomes the domain. Now, look at this. If I ask you to compute something like this, f composed with f inverse of, let's say, A. That is, I'm asking you, what is f inverse of, not A, because of how I define it. Let me say, I want to start with this. Let's say f inverse of f of A. Okay, I want this. Now, the input for f is here. This is the domain, and this is the range. The domain here, the range here. Okay, so in the domain of f, I'm picking A. So f of A is 1. Now, f inverse of 1, if I come to this place, to f inverse of 1 is A. The same thing, if I do, let's say, f inverse of f of C, for example, I will have f inverse of I will start from the inside. Remember, always starting from the inside for a composite function. So f of c is 3. Now, if I find f inverse of 3, f inverse of 3 will be c. Now, you can notice that my answer is the input I have for the composite function. What of the other way around? F composed with F inverse. In this case, now I'm going to consider something like 1 because I'm picking from here now. So that is so F inverse of 1 is A. And now F of A is 1. The same thing if I do F composed with F inverse of, let's say I'm picking 3 as the input. So I will have F inverse of 3 is C, and F of C is 3. Again, we can see this. So every one-to-one function has this property. That is, when we have F inverse of F of X, for example, we say it is X, and F, let's say, composed with F inverse of, let's say, X, I still claim it is X. My X is arbitrary, could be anything. However, now, before that, we have been able to define inverse of our trig functions, which means we should be able to do that. However, we need to be careful because we are working on restricted domains. So I write, for any trigonometric function, f composed with f inverse of y is always y for all y in the proper domain of the given function. Let us break it down. We are dealing with trig functions. So remember, f inverse is going to take ratio as inputs, and it is going to give angle as outputs, right? Now, f acting on angle will give us ratio. So, because our final answer is ratio, we say, okay, that works well every time for when y is in the proper domain for the given function. Okay. This follows from the definition of inverse, just like I just, explained over there. And from the fact that the range of f was defined to be identical to the domain of f inverse of to f inverse. However, we have to be a little more careful with expressions of this form. Why? Because when I compute f of x, I am getting a ratio. Now, when f inverse acts on that ratio, I'm going to get angle. But remember, for example, if I have something like this, for sine is restricted to negative pi over 2 to pi over 2. Now, what happens if my angle is somewhere here? What happens if my angle is somewhere here? That is outside negative pi over 2 to pi over 2. It turns out that I cannot claim that it is going to be x because I'm working within a restricted domain of that function. Now, in general, we say that if we have this situation again, sine of composed with sine inverse of x, whereby the input for sine inverse is ratio, and sine of that ratio is sine inverse of ratio is angle, And sine of angle is going to give us ratio. So in that case, we say that is fine. It is x for when our x is between -1 to 1. And also for cosine, it holds when x is between -1 to 1. And for tangent, it also holds when x is from -infinity to +infinity. However, when our output is angle, we have to be careful. It only works only for when x is within -pi/2 to pi/2. For cosine, from 0 to pi, and for tangent, from -pi/2 to pi/2, without the endpoints being included. I hope that makes sense. All of this follow from our previous class on how we determine the restricted domain we work with. Here is a question. Is sine inverse of sine of x equals to x? Question mark. Let us see. Whatever we are getting here is going to be ratio. And when sine inverse acts on ratio, we get angle. That will not always be true. Why? Because sine inverse is working on a restricted domain for sine, which is -pi/2 to pi/2. So it is not every x that will work in that case. For example, consider the case we have here. Can we say this is true? No, that is not true, because this guy, so we say not true, since 3 pi/4 does not belong to this restricted domain for sine. Or we say it is not in the range of sine inverse. Okay, now given an expression of this form, where f of theta equals to sine theta, cosine theta or tangent of theta, to evaluate that, if theta is in the restricted domain, then this is always true. F inverse of composed with f of theta is theta. And if not, then you need to find an angle within the restricted domain of f such that they will be the same. Okay, I will break that down using example. Let me break that down using example. Example 1. Evaluate the following. Sine inverse of sine inverse of sine of pi/3. Let us see if we can apply our rule here. I can make this claim that this answer is pi/3 without much work. Why? I need to give reasons. Since pi/3 belongs to this range of sine inverse, or to the restricted domain of sine. So pi/2. Done. That is it. Let us consider the second one, sine inverse of sine of 2 pi/3. Now, here, our answer is not going to be 2 pi/3, since that value does not belong to -pi/2 to pi/2. So what do we do then? We need to find an angle that falls within this range of sine inverse. So to do that, let's see. Now, we can start with the inside function sine of 2 pi over 3. We can start with that, which is, so from here, sine of 2 pi over 3. We have our unit circle here, 2 pi over 3. Sine of that is root 3 over 2. So which is root 3 over 2. And then we say sine inverse of sine of 2 pi over 3 becomes sine inverse of root 3 over 2, which is, and like we did the other time, sine inverse of root 3 over 2. That is, we are looking for that angle such that the sine of that angle is root 3 over 2. So there is one here, sine, which is pi over 3. So that is pi over 3, or which one again? 2 pi over 3. 2 pi over 3. However, this does not belong to negative pi over 2, comma pi over 2, as we claimed earlier. Therefore, our answer is, so we say this 2 pi over 3 equals to pi over 3. Answer. So, that is that. That is that. Okay. You can use different methods to get into getting that angle. But this is one way. This is one way, which is a very general method. That is why I like sticking to that. So another one, let us see, cosine inverse of cosine of 2 pi over 3. Cosine inverse of cosine of 2 pi over 3. Okay, in this case, let us see. Our claim is, in this case, I will claim that my answer is 2 pi over 3. That is my claim. How do I know that? Since 2 pi over 3 belongs to the restricted domain for cosine, which is 0 to pi. That is, we have this angle in the restricted domain of cosine, meaning cosine inverse is fine. That is, 2 pi over 3 is 120. 120 is between 0 and 180. So it is fine. So that is it. That is it. We are done with that. And lastly, I'll write it here. Let's see. Cosine inverse of cosine of negative pi over 3. Again, there are several ways we can solve this. Let us be careful. Here, I will say my answer is not negative pi over 3, since that angle does not belong to the restricted domain of cosine, which is 0 to pi. So it does not belong to that. That is not my answer. However, look at this. Observe. We observe that, let us use one of the things we know. Observe the cosine of negative pi over 3 is the same thing as cosine of pi over 3. How do I know this? Because cosine is an even function. It's an even function. We can use that, right? Now, if that is true, that implies that cosine inverse of cosine of negative pi over 3 is the same thing as cosine inverse of cosine of pi over 3. And now my claim is that my answer is pi over 3. Why? Since that pi over 3 belongs to, let me write it very well, since pi over 3 belongs to this restricted domain, pi, 0 to pi. 60 is between 0 and 180. Done. So, guys, it is as simple as that. So you should pause this video and write this, try it, and work on it by yourself. Look at this. This is not in the restricted domain for sine, meaning you need to find an angle such that it is going to be, coterminal with that's 5 pi over 6 for sine. Then you evaluate that. And it will be in negative pi over 2 to pi over 2. So, and this, think about this as well. Pi over 8. All right, let us look at another example. Evaluate tan inverse composed with tangents of 11 pi over 9. Here, my claim is that this is not 11 pi over 9. How do I know that? Since this value does not belong to the restricted domain of tangents. Remember that here has to be open because at those points, tangent has asymptotes, vertical asymptotes. So it has to be open. Now, what do we need to do? We need to find another angle. One way to do that, we cannot find pi over 9 in the unit circle. It is not a special angle. Well, we can do this. We know that tangents as a period of, you should be able to say that before I write, period of pi. Okay, that implies that we can find another angle that is coterminal with 11 pi over 9 for tangents. That implies that tangents of 11 pi over 9 is the same thing as tangents of, let's say, 11 pi over 9 minus pi. Because I want to bring it into negative pi over 2 and pi over 2. So I just subtract pi from each. And now I will have, okay, interesting. So I have, okay, my pen is not writing. What is wrong? Interesting. Okay, tangents of, so this is, I can just quickly do it. 11 pi over 9 minus pi, which I can write as 9 over 9. So which is 2 pi over 9. So that is 2 pi over 9. Let us think about this. Pi over 9 is about, so pi is 180 degrees divided by 9, that is 20 times 20, that is 40. 40 belongs to this place. We can find 40 here. So we are good. That implies that tangents inverse of tangents of 11 pi over 9 is the same thing as tangents inverse of tangent of 2 pi over 9, which is the same thing as 2 pi over 9. Since 2 pi over 9 belongs to negative pi over 2 comma pi over 2. When you write your math this way, your math solution this way, it helps you to keep the understanding of what is going on. Okay, let us briefly look at other forms of composition. Up to this point, we have looked at this form, F, something like this, right? We did not bother to look at this form because we know that it is always x. So far, x is defined from -1 to 1, for example, for sine and for cosine, and from -infinity to +infinity for tangent. So it is trivial. So far we've been looking at, sine, sine inverse, or sine inverse sine, cosine inverse cosine, tangent inverse tangent. Now let us look at when we have different trig functions. That is what we want to look at now. That is maybe sine and cosine. Guys, what we did earlier is not going to work here. Even if we have a situation like this, let's say sine inverse of cosine of pi over 3. Even as pi over 3 is in the restricted domain of cosine, we will not do that. Rather, we are going to solve it using one of the methods we have used earlier today. So in this example, let us solve this. Sine inverse of cosine of 13 pi over 6. I will solve this by letting I will solve this by letting the inside function cosine of 13 pi over 6, I will let it to be some angle A. So what is this? Even maybe this is not important. I can just solve, let me rewrite it this way. I can say let A equals to cosine of 13 pi over 6. Okay, so this is, we all know how to find this. 13 pi over 6 is outside one rotation. So we need to find a coterminal angle that is the same as 13 pi over 6 for cosine. And that is, quickly do it here, 13 pi over 6 minus 2 pi. The period of cosine is 2 pi. I can make this 12, then over 6. So that is pi over 6. Good. So which is cosine of pi over 6. And cosine of pi over 6 is, what is that? Cosine of pi over 6, that should be root 3 over 2. Okay, so we have sine inverse of cosine of 13 pi over 6 to be the same as sine inverse of cosine pi over 6 is my A. So now I have sine inverse of A, which is sine inverse of, our A now is square root of 3 over 2. So just let us do what we have been doing. That is, if we go back to our unit circle, so here where I can just take this guy and drop it there. Um, then I have, okay. Okay. Um, from the unit circle, I have that for sine root 3 over 2 here. So that is pi over 3. And also root 3 over 2 to pi over 3. So I have those values. I have pi over 3 or 2 pi over 3. However, remember, now for sine inverse, this will not work since it is not within this restricted domain for sine, or what we can call the range of sine inverse. Therefore, our answer is, we claim that sine inverse of cosine of 13 pi over 6 is pi over 3. Answer. Okay. That is that. So I will leave you with this to try. Do the same thing. Do the same thing. Find a coterminal angle and just do the same thing. So pause this video and um, find your answer. Okay. Sure. This should be G. Okay, inverse. Okay, all right. Now, we want to consider composition of this form. So the other time, we looked at composition of F inverse of F. Then we proceeded to we proceeded to something like F inverse of G, right, of X. Then now we want to look at um, composition of this form, F G inverse of X. That is when the inverse is the inside function. And remember, when the inverse is the inside function, remember that the inverse is going to take ratio and give angle as output. So when we have something like this, how do we go about a situation like this? The unit circle will not help me because 4 over 5 is not part of the special ratios I have on the unit circle. Okay, I can do this. Again, we go to the inside. I can say, let's cosine inverse of 4 over 5. I can call it some value A. What does this mean? I need some angle such that the cosine of such angle is 4 over 5. That is how we move back and forth um, between a function, a trig function, and its inverse. Now, what does this mean? Cosine of an angle is 4 over 5. But what does that mean? You remember this guy? SOHCAHTOA? Good. So I can do something like this. And say this is 90 degrees. I call this A. Now, cosine is adjacent over hypotenuse. It means this is 4, this is 5. Then I can find this side. I will need it. I can find it. Let me call it Y. So I will have something like this. From Pythagoras theorem now, y squared equals to 5 squared minus 4 squared, meaning y equals to square root, put plus or minus 25 minus 16, which is plus or minus square root of 9. And y is plus or minus 3. But we know that this input is positive, okay? That input is positive there, so feels like our angle should be somewhere here or somewhere here. Remember, all students take coffee. So cosine is positive here, positive here. Now, I'm going to conclude that my angle is in the first quadrant. The reason being that the angle that will make this to be here is when we are now outside the restricted domain for cosine. So I can just conclude that my value is positive, right? Now, that is my angle is in the first quadrant, which will make y to be positive there as well. Therefore, we can now proceed to say, therefore, cosine inverse of 4 over 5, which is the same thing as sine of, remember, this guy, we say it is A, which is sine of A. We just need to go back to the triangle. What is sine of A? That is opposites over hypotenuse. So that is 3 over 5 answer. So that is that. What about this? We do the same thing. We can say let tangent of 7 over 4. We say let it be some value, call it A. It means tangent of that angle is 7 over 4. Again, we cannot return to unit circle because 7 over 4 is not a special value on the unit circle, so we can do this. So if I call this A, tangent is opposite, which is 7 now, over adjacent, which is 4. I can call this side, let's call it B. I can call it anything. So from Pythagoras theorem, it turns out that B squared equals to 7 squared plus 4 squared. So which is 49 plus 16. So which is 65, I believe. And B is plus or minus square root of 65. Looks weird. But yeah, it is correct. Okay. Now, it turns out that sine of tangent inverse of 7 over 4 is the same thing as sine of, remember, we have replaced everything inside by A, so it's the same thing as sine A. And what is sine of A? Well, sine of A is opposites over hypotenuse, what we find here. And again, I will claim that my value here is positive. See, tangent is positive here. Tangent is positive. Now, if I again return to this, tangent is positive here. All sine, tan, cos. So tangent is also positive here, right? However, in this third quadrant, it is already outside our negative pi over 2 to pi over 2. So I will just stick to positive. So that is opposite, which is 7 over hypotenuse, which is square root of 65. Oh, well, we always don't want our answer to be in this form, so we rationalize 65, 65, and that is 7 root 65 divided by 65. Answer. So that is that. Okay. Um, the last example here, we do the same thing. You can pause this video and just, try it before you continue. Let our inside function be A. That means that sine of A is x over 3. There is nothing fancy here, nothing too spectacular. It's just, instead of using some number, we put x, that's all. So do the same thing. You're right. No, that's not a good right angle. A right angle, this is better. I will call this A, 90 degrees. Sine of A is opposites over hypotenuse, 3. We can find this. Let's call this B. We can find B, length B. So returning to Pythagoras theorem, B squared equals to 3 squared minus x squared. So B is plus or minus square root of 9 minus x squared. Please do not say the square root of 9 is 3. The square root of x squared is x. No, you cannot do that because you have minus in between. So leave it that way. That is why now you can see why we give you this interval, the domain where x is defined. It is only defined for -3 to 3 because if, okay, yeah, because if x is, let's say, -4, so we have -4 squared, which is 16, 9 minus 16, we will end up having negative inside the radical. So that is why we give this domain where x is defined. That is what that interval is doing there, telling you how x is defined. It is not for every value of x. It is just for this domain of x. That being said, now we do know that we can say cosine of sine inverse of x over 3 now is cosine of, we've represented all of these by A. So cosine of A, which is cosine of A is adjacent, which is B. Our B is square root of 9 minus x squared over hypotenuse 3. So again, we are done. It is as simple as that. So you go ahead and pause this video and solve these 3 problems. So it should be easy for you to handle. And guys, I will be ending this video at this point. So I will see you in my next video. Keep having fun with maths. Bye for now.